So it's my pleasure to introduce Mathie, who, my German is not good, is joining us from the Ludwig Maximilian University in Munich. He's going to be talking about black holes and analogies.
Thanks so much, Bonn. Thank you, first of all, for the invitation to come and speak at the BHI, and for joining me early on a Monday morning as well. This is a sort of a difficult slot, I guess. The weekend is a hard act to follow. And hello to people on Zoom as well. So as Helen says, I'm Alex. I'm a philosophy PhD student at the LMU in Munich, at the Munich Center for Mathematical Philosophy. This is actually my second week back doing academic things. I took a 2-year break from my PhD, and I've recently just come back to the University of Bonn this time, doing a Heinrich Hertz fellowship, where I'm hoping to sort of like wrap up some of my PhD research. So naturally, I'm really excited to be here with you today. I'm also a little bit nervous because this is the first time I've thought about any of this stuff in a little while. But I'm really looking forward to digging into it with you and getting some useful feedback on this stuff. Just bear with me if I'm a little bit rusty. I've thought about this stuff in a little while. So today, I want to talk about black holes, analogical reasoning, and some of the ways in which analogies are used and kind of get tied together in black hole physics. But before we start, I want to take a few moments to kind of motivate exactly what I want to talk about, to give you some sort of spoilers, I suppose, about where I'm trying to go with this talk, just so you can sort of bear those conclusions in mind as I'm sort of moving towards them throughout the talk. So in the spirit of getting my excuses in early, as I've said, like I'm not a physicist. I have a bachelor's degree in physics, but it's been a long time since I sort of sat down and studied physics in any sort of like rigorous way. So today is kind of very much a sort of non-technical conceptual analysis of what I'm calling here the sort of conceptual structure of black hole thermodynamics. So I think that is still interesting and important for 3 reasons. The first is I think it's kind of novel in the sense that those of you who have kind of engaged with the literature on analogical reasoning in black hole thermodynamics, there's been some really interesting publications on the status of the analogy between the laws of thermodynamics and the laws of black hole mechanics. There's been some really interesting literature on the analogy that underpins analog experimentation, but I don't know of any work that tries to sort of connect the two and tries to show how those 2 analogies kind of bear on each other, and that's kind of what I want to talk about today. And in particular, I want to argue that the way that these things interact with each other, these 2 analogies, leads to this sort of interesting tension. And specifically, I want to say that this tension is kind of permanent-ish in the sense that I don't think it's going to be ameliorated by progress in experimental physics. And lastly, I think this is interesting because it seems to actually contradict positions that are held by philosophers and physicists, as we shall see later in the talk. So it does seem to have sort of consequences for what I take to be the attitudes of practicing scientists and philosophers as well. Okay, so I referred on the previous slide to this sort of tension. One way to see this is to put what I want to say in the following way. So today I want to argue for the following syllogism. So premise 1, I want to argue that belief in the physical significance of the black hole thermodynamics analogy depends upon belief in the existence of astrophysical Hawking radiation. Premise 2, belief in the existence of astrophysical Hawking radiation depends upon the epistemic legitimacy of analog gravity. And it follows directly from those 2 premises, with maybe the sort of weak hidden assumption that this depends upon relationship is transitive, that belief in the physical significance of the black hole thermodynamics analogy then depends upon the epistemic legitimacy of analog gravity.
So I have a question.
Yeah.
You say astrophysical Hawking radiation.
Yeah.
Is that different from just Hawking radiation? I mean, something makes it astrophysical?
So I mean Hawking radiation in the sense that it's coming from an astrophysical black hole rather than an analog black hole.
Okay, analog black hole. Exactly, but a physics black hole is an astrophysics.
Yeah.
Okay.
I think so.
Okay, fine.
Cool. And I want to say that if you believe in this syllogism, if you think this is sound, this conclusion makes it really difficult to combine skepticism about analog gravity with support for the idea that the black hole thermodynamics analogy is physically significant. And lastly, I want to sort of argue that three plausible ways of resolving this tension run into quite severe challenges. I do think there's probably a way through this that I'll talk to later in the talk. But I do think it kind of leaves us with this puzzle of how we should go about reconciling these attitudes. Okay. So my plan to sort of convince you of this, I guess, is as follows. I want to spend a little bit of time briefly talking about what analogical reasoning actually is. Then I want to, on a very sort of like high level, just explore two instances of how this occurs in black hole physics and sort of briefly characterize those two sort of central analogies. And then lastly, I want to demonstrate that A, those instances are related to each other. B, the way in which they are related induces exactly this tension I talked about, where it's very difficult to combine skepticism about analog gravity with sort of support for black hole thermodynamics. And C, I want to sort of explore a couple of those ways that I talked about resolving that tension and show that they run into these issues. And I should mention that this talk is based on a chapter that I was lucky enough to contribute to this really great edited collection on the philosophy of astrophysics that came out last year. It's entirely open access. And what I say in this talk expands on a lot of what I say, or rather the paper expands on a lot of what I say on this talk, like for reasons of sort of, time and brevity, like I've had to sort of be a little bit more sort of schematic in the talk than I am in the paper. So I've included this QR code in case people want to access the paper either now or after the talk, but I hope that the talk sort of gives you the sort of main moves of what I'm trying to do here. Okay. So onwards to sort of the first part of my plan. I want to spend a bit of time just characterizing what I take analogical reasoning to be. And as I say, I don't actually want to spend too much time doing this, just because I don't think we need a particularly thorough account of analogical reasoning to proceed with the later parts of this talk. But useful to just review what I mean when I say this term before we sort of dive into the main points. So analogical reasoning is generally considered to be any kind of reasoning that relies upon an analogy. And an analogical argument is a form of analogical reasoning that essentially points to certain similarities highlighted by an analogy and uses those similarities to support some further inference that some other, like up till now, sort of unobserved similarity holds. So we can schematize this roughly in the following way. We've got two different domains here, and we've got analogues sort of like mapped between the two domains. So you've got P corresponds to P star, Q corresponds to Q star, R corresponds to R star. And then the conclusion based on those pre-existing similarities is supposed to be that some other similarity should be expected to hold. Some other similarity that we know is true in domain 1 holds also in domain 2. So a couple of examples from the history of science to sort of motivate exactly what we mean by this. The first is the discovery of the narcotic effects of a drug called meperidine. So meperidine was known to have a very similar chemical structure to that of morphine. And then it was also observed that when we administered doses of meperidine to mice in the laboratory, their tails curved in this sort of distinctive S-shaped way. And we knew that that was also the case with morphine. So we have these two similarities between the two things. So there's a clear similarity between the chemical structure of morphine and the chemical structure of meperidine. There's a clear similarity between the sort of physiological effects of those drugs in certain doses in the same sort of organism, lab mice in this instance. And we take this to be sort of evidence, or it was proposed as evidence that we should expect meperidine to have the same narcotic effects as morphine. Yeah, go ahead.
Quick question. So I see the analogy in the top part. When people talk about analogical reasoning, do they also draw it as an analogy to the conclusion, or is the conclusion supposed to be in the new context, you would get this conclusion, but independent of the analogy part?
How do you mean exactly?
Like, is the conclusion also supposed to be an analogy kind of conclusion, or is it supposed to be within the domain of the paradigm, you could find this conclusion based on these premises? Does that make sense?
Yeah, I think so. So I guess the way I think about it is like you have these observed similarities, and then you also have this being observed, and that itself suggests that sort of because we've seen observation here has then corresponded to observation here, under the line, like observation of narcotic effects there in morphine suggests that given the similarities above here, we should expect that to hold. Does that make sense?
I guess, but I wonder if, like, if you follow the morphine, you get the narcotic effects conclusion in that column. So, like, I feel like it's kind of independent.
Yeah, absolutely. So, in Mary Hesse's work, for instance, like the way that she characterizes analogy, she distinguishes between horizontal relations and vertical relations. So she would say that what we're doing here is like picking out the sort of horizontal relations between these two domains. But you're right that within each domain you have sort of vertical relations where this and this might sort of fix this to be the case, if you see what I mean. And that might not be the case in different domains. So yeah, like for Hesse, part of a good analogical argument is sort of providing evidence that you would expect the vertical relations to be the same in the domain that you're trying to make the inference in as well, if that makes sense. Cool, great question. So a second example, a little bit closer to home in terms of physics, is Joseph Priestley's original argument of what would later become Coulomb's law. So it was a known result in the case of gravitation at the time that there was no net force inside a hollow spherical shell of uniform mass density. And Priestley, through experiments, observed that inside a hollow spherical shell of uniform charge density, that there was also no net electrostatic force. And he sort of conjectured on this basis that the force law governing the electrostatic case should have the same inverse square form as Newton's universal law of gravitation. And this was later confirmed experimentally, 2 years later, in fact, by Scottish physicist John Robertson, who found through experiments that the force varied with x to the minus 2.06, I think he concluded, or something like that. So this was later sort of borne out by experimental evidence. So in both of these cases we've just seen, the analogy is kind of proposed as a sort of conjecture. Here that, you know, the law has a certain form, and here that we should expect to see these narcotic effects in mice given the paradigm. And that sort of conjecture is later confirmed by direct empirical evidence, essentially. And it's a sort of it's kind of a matter of controversy what analogical reasoning is actually good for. So you've got some people who think that analogical reasoning can only ever play this kind of heuristic role where, you know, it leads us to make certain conjectures, and then later down the line we replace those with sort of firm empirical evidence. But equally, there are people who argue that analogical reasoning can itself be a form of evidence. And similarly, there's really substantial literature on how we should distinguish good analogical arguments from bad analogical arguments. So that kind of comes back to what I was just saying about Hesse, like, you know, thinkers like Mary Hesse, Paul Barther, John Maynard Keynes and stuff like that have done a lot of thinking about how to characterize. In fact, John Norton's got a really good recent book on how to characterize sort of analogy as well. I want to set this question essentially to one side for this talk. Like, I'm not interested quite so much in is the analogy for analog gravity a good analogy? Is the analogy for black hole thermodynamics a good analogy? I'm more interested in how those two things connect. And I'm particularly interested in the fact that in both of those instances, we seem to have an analogy being provided as evidence, not just as sort of conjecture. So I'm specifically interested in the following case, like when analogical reasoning is supposed to play this evidentiary role, and the premises of of the analogical argument are taken to provide actual evidence for its conclusion, rather than just a sort of hint that maybe we should explore that in more detail.
Good question.
Yeah.
Is there an alternative example in science where this is done, like analogy meaning evidence?
Good question. I can't think of one off the top of my head, but I feel like I have have seen other examples. I mean, so I'm racking my brains to think of an example. I'm sure there is one. Let me get back to you on that. But I think what like the instances in which we often find people proposing analogical reasoning as sort of evidentiary are those cases where we have very limited sort of empirical access to the system in question. So I guess you can start to see why it becomes of interest in the black hole case. I know Kareem Tebo has argued with Pete Evans as well that like stellar nucleosynthesis is another example of something where like we don't have that kind of empirical access and we have to rely on sort of non or indirect sort of empirical evidence such as analogical reasoning.
I have a quick one with it.
Yeah.
I don't know if it's quite exactly what you want, but there's a paper that does laboratory astrophysical shock experiments. So like set up a fluid with different densities and propagate a shock fluid. And they say, oh, this is like an analogy for the inside of a star and shock happening. It's a little bit more robust than analogical reasoning, but it's kind of a weird.
Cool, thanks. Okay, great. And I want to explore sort of two putative instances of analogical reasoning playing exactly this kind of evidentiary role in black hole physics. So the first is black hole thermodynamics, where you have this really quite remarkable formal analogy between the laws of ordinary thermodynamics and the laws of black hole mechanics, which, with the addition of certain critical results in semi-classical framework, seems to kind of support the idea that black holes and thermodynamical systems are linked in some sort of deep and profound way. And secondly, we have analog gravity research, where similarities between the kinematics of analog black holes and astrophysical black holes are taken to support the existence of astrophysical Hawking radiation, so Hawking radiation from an astrophysical black hole. Okay, so that was a kind of rough sketch of what I take analogical reasoning to be. In part two, I want to sort of roughly sort of schematize two instances of analogical reasoning in black hole physics literature. And I'm really conscious that I'm probably the person in the room who knows the least about these things. So yeah, if there are sort of major flaws in what I'm saying, obviously let me know. But I think it's fine to kind of just characterize these things quite broadly. I'm not aiming for a sort of deep technical sort of like explanation of what's happening here. I just want to show that this sort of like roughly fits the mold of what we were just talking about in terms of analogical reasoning. So the first of these is, as I just said, black hole thermodynamics. And the starting point for this is the discovery in the early 70s by James Bardeen, Brandon Carter, and Stephen Hawking, that there is this fascinating sort of mathematical analogy between the laws of thermodynamics and the laws of black hole mechanics, as shown here. And we can see in these equations that you've got the surface gravity of the black hole, kappa, sort of playing the same mathematical role as the thermodynamical temperature, T. Similarly, we've got the black hole's surface area playing the same role as a thermodynamical entropy. And we've got the black hole's mass playing the same role as a sort of thermodynamical energy. And the last of these is already quite a significant clue that there might be something sort of physically substantive to this analogy rather than it just being a sort of mathematical curiosity. Because we know that in relativity, there is this celebrated kind of mass energy equivalence. So that might already make us think, this is interesting. We seem to have this sort of correspondence between mass and energy in this case. Maybe we should take the other correspondences seriously as well. So to really crudely kind of put this putative analogical argument for black hole thermodynamics at this stage, we can just point out these correspondences. So we've got, T and kappa corresponding, we've got U and M corresponding, we've got S and A corresponding. And we might think, well, this is sort of a clue, I guess, that thermodynamical systems are in some sense similar to black holes, or indeed that, black holes are just thermodynamical systems or can be treated as thermodynamical systems.
Can you name the physical quantities behind the letters?
these three?
Oh, of course. Yeah, yeah, yeah. So we've got temperature on the left-hand side. We've got surface gravity on the right-hand side. We've got the internal energy and mass. And then we've got entropy and area, surface area of the event horizon. Yeah, so we've got this sort of putative correspondence, but there are several reasons to kind of resist taking this seriously at this stage. So classically, you know, the idea is that like this isn't really this is sort of a bit of a non-starter, I guess. So for a couple of different reasons. One is that it's really difficult to make sense of the idea of interaction on this picture. And for a theory like thermodynamics that is fundamentally about like interactions between systems or systems in the environment. In the black hole case, in classical relativity, the global definition of a black hole as the boundary of the causal path to future non-infinity makes it very challenging to see how any kind of like local observer could delineate where the system is in the first place. It's a global feature of the space-time rather than a sort of locally definable thing. And secondly, we might worry as well that interaction and the exchange of energy requires us to be able to kind of like localize energy. But this is a sort of notoriously vexed issue in general relativity. How do you localize stress energy? And the other issue that prevents sort of taking this seriously in the classical case is this sort of really critical disanalogy between temperature and surface gravity. So I guess.
Do you take it for the case to be that if it's not a full analogy, it's not an analogy? I mean, is there room to have something that says this is analogous in the following properties, but not those other properties?
Yeah, good question. So I think it probably depends on what you want the conclusion of the analogical argument to be. You see what I mean? So I think where I'm trying to go with this is that these disanalogies sort of preclude the conclusion that this analogical argument is trying to draw at this point, right? So if we were arguing for a different conclusion from these observed similarities, then maybe some disanalogies would be totally permissible and they just don't bear on the question of similarity. But this one seems to. So yeah, the sort of second challenge here is that there is this sort of critical difference between temperature and surface gravity, and that can be seen kind of intuitively by thinking that in the classical framework, a black hole is a perfect absorber, incapable of kind of emitting any form of radiation. And so it seems that insofar as it makes sense to attribute a thermodynamical temperature to that object at all, that temperature should be absolute zero just on physical grounds. And so it's very difficult, I guess, to take seriously the idea that temperature corresponds to surface gravity when, for a black hole with non-zero surface gravity, it seems to make sense physically to give it in the classical framework thermodynamical temperature of zero, absolute zero. But as will be familiar to many of you, in the semi-classical regime, things look a little bit more promising. So in particular, Hawking in 1974 shows that black holes in fact do radiate with this characteristic temperature that is numerically equivalent to their surface gravity up to a constant. And so this immediately seems to make the analogical argument much more plausible, right? Because it seems to address the issues that we just talked about on the previous slide. So first of all, it just removes this numerical disagreement between surface gravity and temperature. Black holes no longer need to have a temperature of absolute zero. In fact, we've just shown that they have a temperature that is their surface gravity up to a constant. But that seems to sort of substantiate or put back into play this correspondence between temperature and surface gravity. And secondly, we might think that Hawking radiation sort of provides a mechanism through which we can kind of operationalize black holes as thermodynamical systems. So now we have a sense of like how we might begin to understand something like thermal interaction, insofar as it's sort of the exchange of thermal radiation. So now we can sort of enrich our analogical argument for black hole thermodynamics slightly. So we have the same correspondence as before between surface gravity and thermodynamical temperature, between mass and energy, and between horizon area and thermodynamical entropy. And now we have this sort of correspondence where Hawking radiation seems to be, playing the role of blackbody radiation in thermodynamics. And this sort of allows us to much more forcefully make the same point that we were trying to make before, that maybe black holes just are thermodynamical systems. And maybe, the more extreme way of putting it would be that, maybe gravity is just a fundamentally thermodynamical phenomenon, like someone like Padmanabhan thinks. And this seems to be kind of borne out in some of the things that physicists and philosophers have to say about the Hawking effect. So Hawking himself, in the conclusion to his 1974 paper, where he derives the Hawking effect, he says, Bardeen, Carter, and I considered that the thermodynamical similarity between surface gravity and temperature was only an analogy. The present result seems to indicate, however, that there may be more to it than this. Similarly, Robert Wald, in his 94 textbook on quantum field theory and curved spacetime, argues that, the Hawking effect shows that surface gravity truly is the physical temperature of a black hole, and that this, opens the possibility that the laws of black hole mechanics just are the ordinary laws of thermodynamics applied to a system containing a black hole. And then David Wallace has this really lovely paper where he puts the point really vividly. He basically says that quantum field theory and centrally the sort of Hawking effect transform black hole thermodynamics from this suggested analogy into a full equivalence, actually. And then similarly, Chris Ludwig argues that nobody really took Bekenstein's arguments in the early 70s for black hole thermodynamics seriously until Hawking sort of offered this semi-classical argument for black hole radiation. So the point here is that, there does seem to be this sense that it's the addition of Hawking radiation that allows us to take the black hole thermodynamics analogy much more seriously than we could without it. So I want to pause to kind of consider a quick objection. So you might say, well, this isn't an analogical argument at all. Doesn't this just establish that, when we have Hawking radiation, we've got everything we need, right? Black holes are thermodynamical systems. That kind of seems to be where a lot of these things are going. So where does the analogy come in? And I think there's sort of two different ways of pushing back on this. One is that I guess it's not clear to me that even if we had sort of definitive evidence that astrophysical Hawking radiation exists, that this is all we really need for something to be thermodynamical, right? There's no kind of convincing sort of argument as to why having the right kind of radiation is sort of all there is to being a thermodynamical system. And secondly, and I think probably more convincingly, the prospects for direct detection of astrophysical Hawking radiation are actually just incredibly poor. So even if we have a derivation for it, we don't really have any empirical evidence that it exists. And so there's this really vivid way of seeing this. So Kieran Tebo in his 2019 paper argues that seeing or trying to detect astrophysical Hawking radiation is like trying to see the heat from an ice cube against the background of an exploding nuclear bomb. So for a solar mass black hole, the Hawking temperature is of the order 10 to the minus 8 Kelvin, which is vastly smaller than the 2.7 Kelvin cosmic microwave background. So trying to detect that is just an absolute non-starter, at least for sort of black holes on that scale. And so, we might hold out hope that with primordial black holes, the temperature would be much higher and then we might be able to see them. But that's one way of sort of pushing back on this. So I guess in summary, black hole thermodynamics points to these similarities to support the further claim that black hole physics and thermodynamics are in fact connected in some deeper sense. And in the classical framework, this argument is considered by most to be sort of totally untenable, though one notable sort of dissenter to this view is Eric Curiel. We'll see this again actually later in the talk. He argues that black hole thermodynamics can be taken physically seriously, even in the classical framework. But we also saw how in semi-classical gravity, when one can include these sort of quantum effects, including Hawking radiation, the case becomes much, much stronger. But because of these challenges for detecting the Hawking effect, it seems like the argument remains kind of analogical. So a natural sort of next question, I suppose, is how else might we assure ourselves that the Hawking effect is in fact a real physical effect? And here we're going to encounter a second analogical argument, that of analog gravity research. So in the early 80s, Bill Unruh proposed that we might be able to exploit this mathematical correspondence between what he called dumb holes, so acoustic black holes, and the mathematics of astrophysical black holes in general relativity to study astrophysical Hawking radiation using these analog models. And since then, there's been a sort of massive explosion in this research, and analog spacetime models now include fluids, Bose-Einstein condensates, superfluid helium, graphene, ion rings, and so on. And there's this excellent living review by Barcelo et al. That sort of provides a really nice survey of all of the work in analog gravity so far. It's also given rise to, I think, what has to be maybe the best diagram I've ever seen in a serious physics journal. So this is Bill Unruh's diagram of fish falling down a waterfall from 2014, and I think it does a really nice job of kind of illustrating the intuition behind analog gravity, essentially. So the idea here is that in a moving fluid, when the fluid velocity exceeds the speed of sound, then you have this sort of horizon where sound waves emitted behind the horizon, because they're dragged along in the moving fluid, can't escape, essentially. And so the sort of thought behind analog gravity is that if we can make this sort of intuitive analogy between the sort of analog black hole like this and the general relativity black hole mathematically precise, then we might be able to kind of exploit it in a meaningful way and use these analog systems to study the astrophysical systems. And it turns out that we can, in fact, make this analogy mathematically precise. So in this living review paper, Barcelo says the features of general relativity that one typically captures in an analog model are the kinematic features that have to do with how fields are defined on a curved spacetime. And the sine qua non of any analog model is the existence of some effective metric that captures the notion of the curved spacetimes that arise in general relativity. And this is most easily seen by comparing just side by side the acoustic metric here on the left for a dumb hole and the metric for the Schwarzschild solution in panodic all-strand coordinates. And you can see this really sort of apparent isomorphism between these two things. And furthermore, Matt Visser has this really nice paper where he presents essentially a kind of very minimalist stripped back argument for Hawking radiation. And he's sort of trying to identify what the essential features are for a derivation of Hawking radiation. And what he concludes in that paper is that all you really need is the right kind of metric. You need a Lorentzian metric, and you need a kind of apparent horizon, essentially. And he argues that both of those things are actually present in the analog case. And we don't need to get hung up on any of the obvious differences between the acoustic black hole and the actual astrophysical black hole, because they share the right kinematics to give rise to the Hawking effect. So roughly, we can characterize the analogical argument like this. So analog black holes can be described using fields over the Lorentzian metric, and so too can astrophysical black holes. The causal structure of analog black hole spacetimes features this kind of appropriate horizon, so too does the black hole spacetimes at GR. And given Visser's argument that these two things are all that's really required to derive the Hawking effect, then the idea roughly is that sort of observational evidence of analog Hawking radiation in the analog black hole case should count as evidence for astrophysical Hawking radiation in astrophysical black holes. And this is obviously very rough and schematic, but like this captures the sort of intuition behind it.
In this analog black hole case, you mentioned also that people are using fluids.
Yeah.
So these are classical fluids from which they're getting a quantum radiation.
Yeah. It's literally just water.
Okay.
Yeah.
What is the equivalent of kappa of this water?
Yeah, that's a good question. I'm not sure off the top of my head. I'd be happy to look into it and get back to you.
Is some local acceleration.
We probably solution to
Probably
the.
exactly the acceleration, which becomes kappa.
I like this analogy very much, and I understand it is a joke. But I do see differently. The reason that we couldn't listen to the fish, which is falling down, is because fish do not speak. Like black holes do not radiate out of radiation. That's the solution.
It's a very compelling point. Yeah.
It's still flapping, right? That is speaking. Those signals do or do not reach.
I forgot to mention the best bit about the diagram, which is in the caption to this. Anu explains that these parts here actually aren't fins; they're ears.
Why?
I was thinking that was flapping and making.
And I think they get rotated too, as they fall.
Okay, you
Cool. So setting aside the question of whether fish speak or not, we'll crack on. So yeah, in summary, I suppose what I'm aiming for here is that it seems that the prospects for direct detection of astrophysical Hawking radiation are just incredibly poor, essentially verging on the physically impossible. Analog spacetimes are sort of claimed to provide a way of probing Hawking radiation despite these challenges. And analog gravity seems to rest on the argument that certain observed similarities between analog models of gravity and actual gravity provide evidence for the existence of further similarities. So in particular, these sort of kinematic similarities that we saw between analog black hole spacetimes and black hole spacetimes in GR sort of underpin this argument that we should expect this further similarity to hold. And namely that the observation of Hawking radiation in analog black hole systems provides evidence for the existence of astrophysical Hawking radiation. Okay, so to sort of tie these things together, so far we've sort of seen what analogical reasoning is, and I've sort of sketched two instances of analogical reasoning in black hole physics, so black hole thermodynamics on the one hand, and analog gravity on the other. And these are clearly very distinct in the sense that they use different premises to argue for different conclusions. So they're two distinct analogies. However, there's clearly this relationship between them. And the common thread that sort of relates them is Hawking radiation. So why does this matter? Well, I think one way of putting it is that absent some alternative story about why we should believe in the existence of astrophysical Hawking radiation, it seems like the success of black hole thermodynamics now seems to be tied to the epistemic legitimacy of the analog gravity program. And you'll notice here that I say absent some alternative story, because I do think that there is sort of ways, room to get around this problem, basically. So, in particular, if we can provide an alternative story about why we should believe in the existence of astrophysical radiation without appealing to analog gravity, then we're not going to be stuck in this sort of tension that I'm aiming for. So we now have kind of all of the resources to kind of state the position that I said I was going to argue for at the beginning, which, to recap, is the following argument. So premise one is simply that belief in the physical significance of the black hole thermodynamics analogy depends upon belief in the existence of astrophysical Hawking radiation. And we saw that by sort of looking at how it seems like you can't really take the black hole thermodynamics analogy very seriously when you only have the resources of classical relativity. But in the semi-classical framework, and specifically when you have Hawking radiation, that seems to give you the sort of conceptual tools to sort of really sort of endorse this claim that black holes are just thermodynamical systems. Premise two belief in the existence of astrophysical Hawking radiation depends upon the epistemic legitimacy of analog gravity. Again, like we saw this before, like the prospects of directly detecting Hawking radiation are essentially nil. And so believing in the existence of astrophysical Hawking radiation, it seems like we might say analog gravity is our best bet. And it follows from this, if you're willing to grant that this depends upon relationship is transitive, that belief in the physical significance of black hole thermodynamics analogy depends upon the epistemic legitimacy of analog gravity.
So just to be sure, what you're saying is this chain, logical chain, implies that if somebody now does an experiment with analog gravity and sees Hawking radiation, zip, the whole thing is validated right up to the top, is that?
Am I saying that?
That's the way I'm reading what you're telling me.
So I guess I'm saying that analog gravity being epistemically legitimate. So us granting that analog gravity can provide evidence of astrophysical.
Right. So let's say I do the experiment now,
Yeah.
right, with the fish and the waterfall and all that.
Mhm.
And upstream, I see Hawking radiation with the correct temperature,
Mhm.
which we haven't yet figured out what it is, but it's somehow some formula that tells you what it should be.
Yeah.
And you actually measure it.
Yeah.
Then bang, 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 it goes up all the way to the top and say, that's it, black hole thermodynamics is fine.
So I guess I probably wouldn't want to say it quite so, like, I don't think that would be sufficient necessarily, but I think it would be a necessary condition.
Okay,
So I think having,
okay,
yeah. So I think if you take the results of that experiment to be evidence that astrophysical Hawking radiation exists,
Yeah.
then you have the means to say, I take the black hole thermodynamics analogy physically seriously because I think I have proof here of the existence of astrophysical Hawking radiation. But if, for instance, you are skeptical about analog gravity and you do that experiment and you find there's Hawking radiation, you find it's at the right temperature, but you say, well, it's just water on a tabletop. Like, what does that tell us about black holes in space? Then I don't see how you have the resources to then say, I still take black hole thermodynamics analogies physically seriously.
okay. And it works the other way too. I do the tabletop experiment and I don't see the Hawking radiation. I still won't rule out Hawking radiation because there's only water on the table.
Yeah, it's a good point. Yeah. But I suppose that doesn't necessarily make us. I mean, then I guess the question is just still open about whether astrophysical Hawking radiation exists, right? But yeah.
Okay.
And yeah, furthermore, like I think there actually does seem to be a discrepancy between how seriously these two things get taken. So analog gravity on the one hand and the significance of the black hole thermodynamics analogy. So two examples, I guess, like one is Chris Butrick, who we've seen earlier in this talk. He concedes in his 2019 that there is some support for the idea that black hole thermodynamics is physically significant, but elsewhere argues really sort of forcefully that analog experimentation just does not work in a confirmatory capacity. And another example would be Daniel Harlow, who I think in Quantum magazine made this quote that I sometimes wonder whether he regrets, because I feel like people have sort of pounced on it and sort of taken this to be a sort of firm philosophical statement of his beliefs. But you know, he sort of dismisses analog gravity as this amusing feat of engineering that isn't going to tell us anything about black holes, but is you know, clearly a sort of very prominent player in research on black hole thermodynamics. And so there does seem to be this sense in which there are certain people who want to sort of deny the epistemic legitimacy of analog gravity and yet somehow still endorse the physical significance of black hole thermodynamics. And I want to quickly sort of gesture at three ways that we might try to resolve this tension, because I think it's in our interest to try and make sense of like what underpins these attitudes. So the first is what I'm going to call naive formalism, essentially, because it locates the solution to this dilemma in the mathematical formalism itself. And in fact, I'm going to argue that it does so to such an extent that it ends up collapsing into a kind of Pythagoreanism, which I think is going to be unpalatable for most people. So the naive formalist rejects the syllogism because they reject this one, but they reject it in this sort of specific way. So they think that the statement, black holes are thermodynamical systems, should be understood as a kind of mathematical claim. And what this means is that for the naive formalists, the existence of astrophysical Hawking radiation is sort of neither here nor there, right? Like what matters is that we have a robust mathematical derivation of Hawking radiation, and that this is enough to kind of establish that Hawking radiation exists, essentially. And that gives us the means to sort of say black hole thermodynamics should be taken seriously. But this,
I just see the word is understood as a mathematical.
yeah, so what I'm thinking here is that, so I think the sort of the mainstream way to interpret the claim black holes are thermodynamical systems is that black holes up there in the sky are thermodynamical systems. I want to characterize this position of saying black holes understood as, you know, specific solutions to the Einstein equations, those are thermodynamical systems. So interpreting both of these things, black holes and thermodynamical systems, as mathematical objects rather than as.
I suppose you said, you know, in the history of energy conservation, each new generation for many generations would say, okay, we found this new phenomenon. We will extend the notion of energy to include like the Brownian fields or, you know, other things. We add a term to this, and so keep energy conservation as a strong principle of foundational aspect of physics and first law of thermodynamics. And it turns out to be productive and generative of new phenomena. We learn how to convert energy between different modes. And suppose you said, okay, that's what's going on here. We have notions of thermodynamics. Black holes appear, seems to create a problem. Bekenstein adds this term to make things, Hawking develops the semi-classical thing. It begins to get more and more. And so now, I don't know that I'd call that exactly mathematical. I mean, that seems to be an extending of the principle, and then the kind of the proof is in the pudding. Does it help us make reason further and learn about? For instance, people who calculate try to use microstate calculations to determine, you know, to actually reproduce the putative. Right. So the putative entropy. So yeah, I mean, mathematical makes it sound like it follows in a purely logical way. It seems to me to follow by the driving force of our commitment to these larger structures, and then get it, you know, it either is productive or it's not. And it seems to be productive. Looking for the factor of 4 seems.
Yeah.
So, you know, what I see a lot, I mean, the claim with Daniel Harlow and others seems to be one a lot of physicists think, that is to say, they do think that black holes are thermodynamic objects, but whether water in a pipe or fish on a cliff or dense matter systems, they're not so.
Yeah. So it feels to me like actually what you're saying is going to be on a couple of slides from now. Like, so I think that essentially this is a really flat-footed way to sort of motivate this sort of mathematical idea. Okay. And I want to sort of just say up front that I don't think this very flat-footed way of stating works. I think you can refine the position quite a lot, and I think that would probably be a little bit closer.
And also, just to say, it is of no significance that I have to leave at 10:30. It just means I have a Zoom call.
He's going to be talking about cardinals.
Yes, I think I have exactly the same problem, and I will ask again your question, but in a kind of a very specific way. In semi-classical derivation of Hawking radiation, we have Planck constant. What is the analogical constant in this hydrodynamical acoustic. And of course, Planck constant is very important because equations are fine, but then we have kind of physical intuition. And Hawking radiation is the because energy goes not continuously, is radiated not continuously in portion in quantum, and Planck constant is there. What is the Planck constant in this acoustic analogy?
Yeah, so I'm not sure in the case of classical analogs for black holes, but they're like a lot of the analog spacetimes are quantum in nature. So I guess like some of the stuff that I think has been done on like yeah, there's all of these other sort of like analog black holes that I think use quantum fields rather than classical fields as well. So I guess in some of those models you might still have the Planck constant. But I'm not sure. I think it's a good question, and I think actually it kind of comes back to this point that Visser makes about like so there's actually loads of differences between analog black holes and astrophysical black holes, and I think it's natural to be worried about whether those differences sort of mean that we should reject this sort of inference from analog black hole analog Hawking radiation to astrophysical Hawking radiation. I guess I take what Matt Visser is saying is that like, so I guess I take Matt Visser to be arguing for the fact that we can set aside all of those values, right? All we need is the right kind of kinematics, and actually that, and we're away. So hopefully that helps.
I don't think I agree with you. What you call the right kinematic is necessary. So the presence of the horizon is necessary for Hawking radiation. But equally necessary is Planck constant.
Right.
And I do not see Planck constant in this acoustic analogy, not because I know it very well and I know that it is not, but I simply don't know. I'm asking for
of course, no, I understand. Yeah.
What is the Planck constant analogy constant in this acoustic black hole?
Yeah, it's a really good question. I'll have to look it up after this talk.
So, Marek,
Yes.
I would say it is both Planck constant and the kappa, because the temperature is finally h bar kappa, right? Kappa being the whatever gravity at the horizon. So there has to be, means the product that finally determines temperature. So in your hydrodynamic analogy, something has to replace the whole thing, I think. You can then try to separate it out into a kappa and an h bar, but the temperature or the amount of radiation depends only on this one constant. And you need a dictionary to translate somehow. And I'm waiting for that. Yeah.
I have an even more basic question actually. Like, so is the Hawking radiation in the analog spacetimes, is that light-like radiation or is it sound waves?
It's sound waves
Sound waves.
in the acoustic case, but I think there are optical ones as well. So in the Bose-Einstein kind of state.
Quantum sound waves for the H bar.
It's finding a spectrum of waves,
Right.
which must be thermal in some sense with some temperature. And I am
But you
not,
also want them to be packets. Yeah.
are you going to actually discuss analog experiments?
No, not in the sort of technical detail.
Has it actually been demonstrated that analog gravity produces Hawking radiation?
So it depends who you ask, right? Like Bill Unruh has this paper called, I think something like has Hawking radiation been observed or something like that. And he argues that like, yes, like the analog models fulfill all of the requirements for Hawking radiation.
And he says that there's a temperature.
Yeah, I believe so.
We should look at that.
Yeah.
What is the temperature and how is it related to Mars?
We have a hard stop at 10:30.
We don't. We can keep going for a couple more minutes. I will say Sakshi has a question on the Zoom.
Yeah, cool. I can say that.
Sakshi, I think we can hear you if you just want to go ahead.
Hi, I want to make sure my question doesn't sort of steal your thunder. So if you're going to talk about what it would mean to reject the other premises, I'll hold off.
Yeah, yeah.
Okay.
Some of that will come out in the wash, but if there are premises that you want to reject that I don't reject in the end, then yeah, feel free to ask at the end, but I do reject some others too.
Okay, sounds good. Yeah.
Cool. So where do we get to? Yeah, so basically I think on a really flat-footed reading, this naive formalism ends up collapsing into a kind of Pythagoreanism, right? So the idea here is that if you think that there is nothing to being, like there's nothing to being a certain kind of thing over and above having the correct mathematics, then it seems like essentially we're endorsing this kind of really radical Pythagoreanism. And I think most people, with some possible exceptions, I guess someone like Max Tegmark maybe might want to be okay with this. I think for the most part, people will want to object to this on sort of independent metaphysical grounds, basically. So we should probably look elsewhere. But as I just said a moment ago, I think the naive formalists kind of, even though they go too far, I think they're probably on the right track here. Just thinking about the mathematics a little bit more. So we can try to sort of sophisticate that, render more sophisticated their position in the following way. So a more sophisticated formalist approach is going to agree with the approach we just saw, the naive formalist, that physical significance can be attributed to black hole thermodynamics on the basis of mathematics alone. But not because they're Pythagoreans, rather because they sort of buy into this idea of non-empirical theory confirmation, which I guess is kind of philosopher speak for just having non-empirical reasons for believing that your theory is like making the correct, or giving you the correct results. And so they might point to some of these things like the fantastic consilience of like multiple different derivations of Hawking effect that we now have. And the David Wallace paper that I referenced earlier in this talk has a lovely sort of run through of multiple different derivations of the Hawking effect. They might also point to universality arguments that suggest that this isn't a sort of artifact of semi-classical gravity, and it will in fact show up in quantum gravity as well. So I have in mind like Polchinski's nice slice argument. And they might also point to other support for physically significant black hole thermodynamics. So they might say, you know, look, we have, as I think it's mentioned a moment ago, like we have things like the microstate counting result from astronomer and buffer. Like that strongly suggests that there are other reasons to take black hole thermodynamics quite seriously. I think the problem that I have with this approach is that they seem to be trying to lower the evidential bar at the same time as sort of keeping it where it is. So it seems like what they want to say is that the sort of theory alone is strong enough to evidence the existence of astrophysical Hawking radiation, but analog gravity for some reason is not. And I think that's kind of plausible, but it seems surprising to me because it feels a little bit like, at least in my head, analog gravity is a sort of quasi-empirical kind of evidence. Like it's not totally theoretical and it's not direct empirical evidence, but it's somewhere between the two. So if you were going to sort of rank the sort of confirmatory power of theory alone, something like analog experimentation and direct empirical evidence, it would feel like that sort of analog experiments should weigh in somewhere between the two. But it feels like the sophisticated formalist is trying to say that theory alone is enough to provide confirmation, but analog gravity isn't, which seems kind of hard to understand, I think. So perhaps a more charitable way to sort of interpret this, I think, is maybe that they're saying that analog gravity doesn't tell us anything beyond what we already knew from theory. So maybe they can say, look, yeah, theoretical evidence is like quite weak, but we have so much of it, and we have such rich theoretical evidence for the reality of the Hawking effect that in sum, when we get analog gravity results as well, it doesn't tell us anything over and above what we already knew. And maybe that's a more charitable way to interpret this position. So I think this is probably what people have in mind. I'd be really interested to know whether that sort of resonates with anyone, and in particular what people's attitudes towards sort of theoretical confirmation is. Lost the clicker, but let's crack on with very quickly a sort of third approach that is quite different to the previous two, that I'll call classical black hole thermodynamics for reasons that will become obvious in a moment. So this rejects premise one, but for different reasons than the naive formalist. So on this view, black hole thermodynamics is already physically significant in the classical regime. And the name that I would associate with this is Eric Curiel, who in his 2014 argues that it's possible to construct the analog of a Carnot cycle between a classical black hole and a thermodynamical system using only gravitational radiation rather than Hawking radiation. And when you do that, what you find is that surface gravity plays the role of a temperature. And sort of taking this broadly sort of functionalist approach, Curiel argues that if it can be shown that surface gravity couples to ordinary classical thermodynamical systems in the same formal way as ordinary temperature does, then there can be no grounds for denying that it is a true physical temperature. And I'm broadly sympathetic to this approach. I think it's nice, and I think it makes sense, especially for something like thermodynamics that is in some sense a fundamentally sort of functional operational theory. But I think one of the biggest issues that Eric himself identifies in this paper is that despite being thermodynamically reversible, in the sense that the entropy remains the same at every step in this cycle, this process actually ends up being irreversible in the sense of black hole mechanics because the irreducible mass of the black hole increases throughout the process. And so you might think that what we've recovered here is mainly is kind of at best a sort of partial unification of these black hole mechanical concepts and thermodynamical concepts, and that there remain these sort of critical decouplings of concepts. So for instance, reversibility here, it seems like we've got one notion of black hole mechanical reversibility and one notion of thermodynamical reversibility, and we've managed to have one without the other. And that might make us question the extent to which this sort of approach by Curiel actually establishes that these concepts are sort of unified in some sense in the classical regime. So very quickly to sum up, I've argued that the connection between the analogical argument for taking black hole thermodynamics seriously and the argument for the existence of Hawking radiation makes it prima facie quite difficult to reconcile support for the former with skepticism about the latter. And I've pointed to a couple of instances where this does seem to be an attitude held by some people. So to me, at least anecdotally, it seems very much more common to disparage analog gravity than it does to disparage black hole thermodynamics. And I think that's been borne out by some of the questions that I've had in this talk. Like, I think people take black hole thermodynamics seriously, but there is sort of widespread concern about whether analog gravity can tell us anything about Hawking radiation. And then I've looked at three different ways of understanding how we might reconcile this tension and resolve the sort of dilemma that I pointed to. But all three of these face challenges. And I think probably the most promising way forward is to develop the sort of sophisticated formalist approach, and in particular to give a more sort of developed account of what work non-empirical theory confirmation is doing in this instance. Cool, thanks.
Thank you, Alex. I can field questions. Maybe I'll ask Sakshi, did you? Yeah, okay, her hand's up. Go ahead.
Hi, Alex. This was a talk that was, so in line with what I do in my research. So it was really fascinating to have another perspective on it. I wanted to react a bit about the second strategy of sophisticated formalism, that's what you called it, to perhaps reconcile this tension of having confidence in black hole thermodynamics, whereas maybe not putting much stock into analog gravity. And, this is partly just my 2 cents, but wondering if this affects how you would want to structure your argument, because I felt like it was sort of jumping the gun a bit, right? That the confidence in black hole thermodynamics was not coming yet from a belief in astrophysical Hawking radiation, but more as, right, a pursuit-worthy program or a guiding principle, if you will, for quantum gravity approaches. So I think there are two elements of your argument that might be subject to interpretation. What do you mean by Hawking radiation? If you mean the original proof of concept that is most closely linked to analog gravity, then I feel like most people working on black hole evaporation are substituting that with Hawking-like radiation because they've gone back to the drawing board. And that would be one reason for them not putting much stock in analog gravity, because they don't think necessarily that, right, substituting the medium is going to give you irrelevant dynamics, which is ultimately what we want. And my, other question has to do with the word depends on. If I were to just, use propositional logic, does that mean necessary or sufficient? Because if you mean necessary, then I think that's relatively easier to reject. If you say sufficient, that might be more palatable, but then the conclusion is not as strong. And the reason I'm thinking, well, yeah, it could be sufficient perhaps if we had, better grounds to tighten the analogy. But let's say sometime in the future, we come up with, a quantum gravitational account of black hole evaporation. We're able to reverse engineer a semi-classical approximation to it. And that approximation has some empirical purchase in a way that general relativity had empirical purchase for black holes long before they were observed because of other predictions, say gravitational lensing. And I'm wondering if we can use cosmology to support, such indirect confirmation that's not outright non-empirical a la Dawid. So I was just curious if you had, thought about that way out for the sophisticated formalist, or, if that might be a little more convincing in reconciling the tension you bring up.
Yeah, thanks. Actually, that's a really, really interesting set of questions. I think to respond first of all to the point about the like depends upon relation, I think like that is a really good point. And actually, in the process of putting together this talk, I kind of reconsidered my position on this. Like,
No.
I actually feel like that might be another really promising way to push back on what I'm saying. And especially what I have in mind is that I feel like the depends upon, if I just skip back to when I last stated the actual like syllogism, yeah, I feel like actually the depends upon relation is different in premise one and premise two. And I think I totally take your point that if you try to strengthen this and just put it in terms of propositional logic, like it becomes a much harder argument to sort of swallow. And I think what I'm probably thinking is that trying to tease out what depends upon really means in the context of premise one and what depends upon really means in the context of premise two would probably shed some light on how to like dismantle this this problem. But the other thing I would say is that I think taking a more kind of almost like a more kind of Bayesian approach to the confirmation here as well would work, in the sense that it feels maybe too strong to talk about necessary and sufficient conditions for something being a thermodynamical system. Maybe what we want to do is just say that, like the Hawking radiation confers some confirmation on the idea that black holes are thermodynamical, and we have to weigh up how the extent of that confirmation compares to the confirmation that you get from the sort of non-empirical theory confirmation as well, and how that compares to what we would have if we could get direct empirical evidence of astrophysical radiation. on your first point, sorry, can you mind just, do you mind just restating what the first question was actually?
Yeah, I was just wondering if someone like Harlow would come back and say, you know, it's a bit strong. The physical significance of the BHT analogy doesn't yet depend upon the existence of astrophysical Hawking radiation. It is more like a guiding principle for pursuit worthiness. But, you know, even to be charitable to the way you formulated your premises, let's say eventually, of course, we want it to be the case that we have an empirical basis to believe in the existence of astrophysical Hawking radiation, then in premise 2, that wouldn't come from analog gravity. Hopefully that would come from some, you know, reverse engineered, more robust version of semi-classical gravity that has indirect empirical purchase, you know, perhaps through cosmological observations. And I'm thinking historically about what happened with general relativity, you know, things like gravitational lensing, you know, lending credence to other thus far non-observed aspects of the theory.
Yeah, so that I think makes a lot of sense. Yeah, like I think, so at the start of this talk, I said that I think this tension is sort of permanent-ish in the sense that I find it hard to see how it could be ameliorated by progress in experimental physics. I think what you gestured to there is exactly one way in which it could be ameliorated, which is, look, we have this clue. It's a bit of an empirical dead end to explore Hawking radiation because we're never going to, like, if what we're looking for is actual empirical evidence, we're never going to get that. Like, let's say that's our attitude. But it might suggest other things that we could pursue, and those things might end up giving us some sort of coherent theory of quantum gravity, and then reverse engineering that sort of provides us with evidence of the physical significance of black hole thermodynamics. I think that's a very reasonable attitude to take. Yeah, I think I probably just agree with you, to be honest. So yeah, I think maybe that does water down somewhat the point I'm trying to make there.
I would like to say something very negative about black hole entropy. We are kind of very keen to discuss Hawking radiation, which is kind of connected to temperature of black holes, which astrophysically are very small, and there are all kinds of difficulties about this. But on the other hand, entropy of a black hole is enormously, absurdly large. Okay. So, of course, I am confident in the classical black hole thermodynamics, but should I care about this classical thermodynamics as an astrophysicist? And my answer to this, and this is where I am very negative, is no, absolutely not. It has nothing to do with astrophysics. Look, Hawking radiation is, of course, cool, fine, it's exciting. But there is this entropy also. When a black hole, real astrophysical black hole decrease, it naively increases horizon area. And therefore, is this important for an astrophysicist? Of course not. Because to see this, I need to wait infinite time. Nothing will cross the horizon in finite, my finite astrophysicist finite time. So I would like to care about black hole thermodynamics and black hole entropy. But how? What what is this black hole entropy? Why should I care if I need to wait infinite time for it to change? And it is not only, I am not technical about this. There is other principle discovered by my distinguished colleagues. Black holes equity. Okay. Accretion rate is fixed, everything is fixed. And in this fixed situation, there are two solutions possible. One, which is Shakura-Sunyaev accretion list.
Correct. I think now
Very,
we
very
are right.
Yeah, very quickly, I will see.
Yeah,
And so very luminous photons are going from the disk to infinity, not to the black hole. And cool, or kind of an other solution, which produces a little amount of photons which directly go to infinity. They go to the black hole, increasing its entropy. And so thermodynamically, it is a very different situation in the sense that in a way, entropy is produced, global entropy is produced on a totally different rate. And there is this beautiful Prigozhin discovery that the real tabletop experiments with thermodynamical systems show us that entropy increases, but it always increases in the slowest possible rate. So is the fact that real astrophysical system always pick up other solution rather than Shakura-Sunyaev, perhaps connected to his Prigozhin principle? And the answer is no. However, in astrophysics, we may also not only talk about Hawking radiation, but about things which are connected with entropy production, etc. However, I do see this problem that entropy increase in real astrophysical situations. When I am an astrophysicist looking at this black hole from a distance, I don't know how to even formulate the fact that entropy production rate is in one situation this and in another this. Now, good physicists who are not astrophysicists, however, are telling me, but Marek, you should be on a different part of the space. Then you will see entropy increase. But my problem is that I am on a specific path. It's not a joke. I understand.
we can do this offline.
We should, yeah,
Set
switch
up the
over.
room, yeah.
But thank you. And thanks, Al.
Thanks, Ivy. Thank you.
You're not around for the day.
Okay, thanks everyone on Zoom.
Yeah, I'll be around for a little bit longer.